So we are in section 2.1, and we're talking about interval notation and then relations and functions. So first of all, for interval notation, if we use the parentheses, we're not including those endpoint values. If we use the brackets, then we are going to use those endpoint values. So if we use some examples here, if we say x is greater than or equal to 7, we include the 7. And then infinity is not a symbol, so we don't include that, so it's parentheses. If we say negative 4 is less than or equal to x is less than 2, we include the negative 4, not the 2. We say x is less than 4, then it's negative infinity to 4. Don't include the negative infinity. We don't include the 4. And then negative 1 is less than x is less than or equal to 5. We don't include the negative 1. We do include the 5. So here, next 1b, we have a relation, and so the domain is all the input values. So 2, 4, 3, but we don't write the 2 again. And then the output values are going to be 3. 3 is repeated until we get the negative 1. Again, we don't write the repeat values. It is a relation, set of inputs and outputs, but it's not a function because we've got two inputs that yield different outputs of 3 and negative 1. And that needs to be true. Every input value has to have a unique output for it to be a function. Moving on to 1D, it is a relation but not a function. And again, we can get an input value of 3 with two different y values, right? You can have 3, negative 1 or 3, 1. And again, every x has to have a unique output y value. So it's a relation but not a function. If we change 1D a little bit with an extension and we say y equals 2x squared plus 1, so we swap the roles of the variables, this is a relation, but it is a function. Now, it is a function because every x value has a unique y value. So negative 3 you plug in, you get 19, negative 2 is 9, negative 1 and 1 are both 3, 2 and 9. Now, if you take a look at negative 2, 9 and 2, 9, it's okay that two different inputs have the same output. It's still a function. So notice the difference between 1D and then 1D, the extension. All right, if we move on to the set of problems in 2, and we take a look at 2a, f of x in this case is a fraction. It's x plus 4 over x squared minus 2x minus 3. The denominator is factorable, so we factor that. And we want to make sure the denominator is not 0. So we set the domain up, negative infinity to negative 1, union, that u is a union, negative 1 to 3, and then 3 to infinity. And we don't include any of those endpoints because we don't want to include the symbols, the infinities, or the numbers, and you can also use the set builder notation. In 2c, we have a square root, and what's inside the square root must be greater than or equal to 0 for it to have a real output. And so x has to be less than or equal to 3 halves. You write it in interval notation. You include the 3 halves, so it's not a strict inequality. And again, you should be able to write it in the set builder notation as well. Moving on to a word problem, we've got a rectangular garden that has a perimeter of 100 feet. We draw a little diagram, and we want to find the area as a function of the width. The perimeter is 2w plus 2l, and so we're going to isolate the l. And we know the perimeter is 100, so you can further write that the length is going to be 500, 100 divided by 2, or excuse me, 50 minus w. And then we replace in the area formula, and we get area is equal to 50w minus w squared. And so the domain, we want to make sure that our output is not negative and not 0. And so we restrict the w value so we don't get 0 and we don't get negative values. And either in the interval notation or in the set builder notation. Okay, for the next set of problems, we're going to be looking at sums, difference, products, and quotients of functions. And if we're trying to find the domain of the new created function, we have to find the intersection of the two functions we're working with. So if we're working with 2x minus 4 and negative 3x plus 6, and let's say we want to find the difference of those two functions, you can just take one function minus another, and we can distribute that minus sign. We get the plus 3x minus 6, we simplify, and so there's the difference of the functions. If we move on to 4D, and 4D will take the quotient of the two functions, and we simplify, and we find that the numerator and the denominator are both factorable. And in fact, there's a common factor in the numerator and the denominator, so we eliminate those. And so the function simplifies nicely to just -2/3. Okay, so those are the function descriptions. But now if we want to find the domain, notice we need to find the intersection of the two domains for the two functions. So let's talk about the domains for both of them. They're both all reals. So the intersection for both of those is going to be all reals. Or you could write -infinity to infinity for 4b. So that's pretty easy. But if we're talking about the quotient, remember there's an added restriction. We don't want the g of x. The g of x cannot be 0. And so the g of x is not 0. That's when x is 2. So we got to throw that out. And so when we describe our domain here, we have to exclude the 2. And of course, if you want, you could use the set builder notation. You should all be able to do that in cases when you're asked to do that. All right, you can also just find these sums, differences, products, quotients at particular values, and you just find the separate functions at the given value, and then you can just combine them. So we find the function at 1, f at 1, g at 1, and then we just add them. Then we get 1. If we take a look at 4g, here we want to find the product of the two functions at -1, so we find them separately. So we evaluate them at -1, and when we plug -1 in for f, we get -6. We plug it in for g, we get 9, and so when we multiply those, we get -54. So we find them separately and evaluate. Moving on to number 5, here we've got two quotient functions. And for 5c, if we want to find the product of the two functions, for f of x, you can just multiply the two functions. And then you can write it as a product down below. And then if we're looking at the domain, remember that the domain here has to be the intersection of these two original domains. So we have to throw out the 2 from the f and the -4 from the g. And so we can write that in interval notation, excluding the -4, excluding the 2. It's the intersection of those two domains. Be prepared to also use the set builder notation. Last example, 5d. If we've got f over g of x, we're just taking the quotient of the two functions, use what we know about division of fractions, and we simplify that. And so there's our quotient. And again, the domain is going to be the intersection of the two, but there's an added restriction, right? The added restriction for the quotient is g of x can't be 0. So that means that x can't be 0. That would make g of x. G of 0 is 0, so we've got to throw that out as well. So we throw out the -4 from the g, we throw out the 2, but we also throw out the 0 from those values. And we can write it in either interval notation, or we can also do that in set notation. Remember, it's the intersection of the domains of f and g. If it's a quotient, we're talking about an added restriction. And that's it.